Before supercomputers and satellite feeds, people still needed to know if a storm was coming. For centuries, predicting the weather meant reading the subtle biological signals happening right underfoot. Take a close look at the ground. If you see ants urgently moving their tiny white eggs to higher elevation, they are reacting to a drop in atmospheric pressure that usually precedes heavy rain. Plants react to the sky too. Pine cones act as natural moisture sensors. When humidity levels rise before a storm, their scales swell and tightly close to protect their seeds. When the air dries out, the scales open back up. These biological reactions are excellent at signaling that a change is on the way. But an ant cannot tell you if tomorrow's wind speed will be 20 kilometers an hour or 50. A pine cone can't give you the exact temperature drop in degrees. To shift from generally sensing a storm to mathematically tracking it, we had to invent tools to measure exactly what the animals and plants were already feeling. This is meteorology, the science of quantifying the atmosphere. This diagram shows the gas layers surrounding our planet. We focus entirely on the lowest blanket of air, the troposphere. Extending 18 kilometers from the surface, this single layer holds the air we breathe and almost every weather system you will experience. The baseline measurement of this layer is temperature. Using a thermometer, we record the exact amount of heat energy trapped in the air. This chart shows a typical daily temperature curve. To understand a day's true weather pattern, meteorologists track the highest peak and the lowest dip. The mathematical difference between these 2 points is called the temperature range, revealing how drastically conditions swing over 24 hours. Alongside heat, the air holds invisible water vapor, which we measure as humidity. When humidity is high, the air is already packed with moisture. This is why you feel sticky on a humid day. Your sweat simply has nowhere to evaporate into the crowded air. A high humidity percentage does not guarantee rain. It strictly means the air is saturated with water vapor at that specific temperature. It's a measure of the invisible load the air is currently carrying. To detect this invisible load, scientists use a hygrometer. This instrument translates the exact moisture content into a precise percentage, known as relative humidity. Pinning down precise numbers for heat and moisture is the critical first step in decoding the dynamic, invisible state of the atmosphere around us. Next is atmospheric pressure. Gravity pulls atmospheric gas molecules towards the Earth, creating a literal column of air pressing down on the surface. We measure the physical weight of that invisible column. Gravity pulls most air molecules down to sea level, meaning that atmospheric pressure physically decreases as you climb higher. At extreme elevations, like Kardungla in the Himalayas, the air is physically thinner and the weight pressing down on you is dramatically lower. To track these pressure changes, we use a barometer. Inside an aneroid barometer like this one, a small flexible metal box expands or contracts as the air weight changes, physically moving the needle on the dial. When pressure drops in one area, heavier, high-pressure air rushes in to fill the gap. That horizontal movement of air is what we call wind. We measure wind in 2 ways. An anemometer counts cup rotations to calculate speed. For direction, we rely on a wind vane or a simple windsock. When fully extended, it gives pilots immediate, visible data on exactly where the wind is pushing. Finally, when the atmosphere cools and can no longer hold all of that condensed moisture, it falls to the ground. Rain, snow, sleet, or hail, it all drops into a rain gauge, where we measure the collected volume in millimeters. With a thermometer, hygrometer, a barometer, a windsock, and a rain gauge, humanity stopped merely reacting to a darkening sky. We began mathematically tracking the mechanics of the atmosphere. Today, these individual measurements are centralized by institutions like the India Meteorological Department. They act as the guardians of weather safety, turning raw data into public forecasts. Mechanical tools are now integrated into automated weather stations. These hubs combine temperature, pressure, humidity, and wind sensors into a single solar-powered unit. Being self-operating, they sit in remote environments like glacial lakes, continuously transmitting data 24 hours a day without a human observer. This diagram shows how supercomputers process that continuous stream of national data to generate actionable warning maps. Meteorologists use a strict color-coded system. Green means normal conditions, yellow advises caution, orange signals an alert, and red mandates immediate action. A red warning for a weather system like this cyclone provides hours or even days of lead time. It gives fisherfolk the chance to return their boats to port, and farmers the window they need to secure their livelihoods before extreme weather strikes. The transition from watching nature's clues to managing a national sensor network has turned the atmosphere from a mystery into a measurable system. These tools allow us to quantify the same shifts that ants and pine cones feel, providing the lead time necessary to protect people and property. When you next notice a change in the wind or a drop in temperature, you are witnessing those exact mechanics in motion.